Welcome to part 3 of our Basics and Types of Bearings video series. In this episode, we'll explore the remaining 4 of the most common bearing types as discussed in our last video. Similarly, we will provide technical details and real-world application examples for each. If you find this video informative and enjoyable, please don't forget to like it and subscribe. Let's begin by exploring our first bearing type, the needle roller bearing. Needle roller bearings are uniquely shaped to fulfill specific purposes. They utilize elongated cylindrical rollers to minimize friction between rotating parts. In terms of load type handling, they excel at supporting radial loads but are not designed to endure axial loads. Consequently, they're not suitable for withstanding combined loads and moment forces. Needle roller bearings comprise an outer raceway, a set of needle-shaped rollers, smaller needles supporting the rollers, and a cage to keep the rollers aligned. Needle roller bearings are known for their exceptional reliability across a diverse array of applications, including internal combustion engines, motorcycles, robotics, and the aerospace industry. When considering bearing selection criteria, we can identify them as outstanding for their compactness, substantial load-bearing capacity, impressive high rotational speeds, and accuracy. However, they are less favorable in terms of noise level and rotational friction. Now let's take a look at a needle roller bearing in action inside an internal combustion engine. First, let's examine an engine block and explore its components. When fuel and air mix and enter the engine, they ignite at the top of the piston stroke, causing the piston to move downward. After descending, the piston returns upward, expelling the combustion byproducts from the engine block. This reciprocating motion is transmitted to the crankshaft by the connecting rod, ultimately being converted into rotary motion. In such high-stress environments with limited space, where precision and durability are paramount, the choice of bearing is critical. As discussed earlier, needle roller bearings with their slender, elongated, needle-shaped rollers excel in such demanding environments. Their precision and compact design are particularly advantageous in applications with limited radial space, like in the crankshaft of an internal combustion engine. Despite their smaller size, these bearings can endure heavy loads, an essential feature in the high-pressure environment of an engine. This ability to withstand heavy loads while maintaining a small footprint is crucial in machinery, where miniaturization, lightweight construction, and precision are prioritized. Moreover, their decreased rotating radius results in reduced rotational torque for the same friction force. Next in our bearing selection is the angular contact ball bearing. Angular contact ball bearings resemble deep groove ball bearings, but are distinct in their shoulder-shaped design on the outer ring. This design enables them to effectively manage axial loads in addition to radial loads. Hence, they demonstrate exceptional capability in providing support for radial, axial, and combined loads. Additionally, they can withstand significant moment loads. These bearings consist of an outer ring, an inner ring, a cage, and set of steel balls. They're commonly found in pumps and compressors, vehicle steering systems, and clutches. When assessing the criteria for selecting bearings, these bearings are notably distinguished for their durability, high rotational speed and accuracy, as well as their low noise level and minimal friction torque. Additionally, they can be characterized as moderately cost-effective and compact. Now, let's put their capabilities to the test by illustrating a real-life application. Consider a centrifugal pump, a type of pump that relies on the centrifugal force generated by the rotation of its impeller to increase the velocity of a fluid. As the impeller spins, it imparts kinetic energy to the fluid, pushing it outwards and converting this kinetic energy into pressure energy, propelling the fluid at high speed into the diffuser. This process not only involves the rapid rotation of the impeller, but also generates significant axial and radial loads on the pump shaft due to the fluid's pressure and the impeller's dynamic forces. Given these operational stresses and the high axial loads particularly, it is crucial to select the appropriate type of bearings for the pump shaft. Upon disassembling the shaft box, we find 2 different types of bearings inside. To support high-speed rotation and manage the shaft's radial load, a deep groove ball bearing has been installed on one side of the shaft. On the opposite side, an angular contact ball bearing is utilized due to its ability to efficiently handle the high axial loads typical in pump operations. The specific angle and geometry of the rings and their shoulders in angular contact ball bearings provide a high axial load capacity, enabling them to withstand both radial and axial loads, as well as moment loads. This capability, along with their design that tolerates a degree of shaft misalignment, makes them particularly suitable for the dynamic conditions of a centrifugal pump. The contact angle variation indicates the axial load, bearing capacity of these bearings, with bearings having increased contact angles capable of withstanding greater axial loads, typically not surpassing approximately 40 degrees. For our third bearing selection, we will introduce you to a bearing type with some distinct characteristics. Self-aligning ball bearings demonstrate a unique advantage in situations involving shaft misalignment or installation errors. They offer moderate radial load capacity, but have poor performance with axial loads, which also applies to combined load situations. The self-aligning bearing can handle minor to moderate moment load. These bearings have 2 rows of balls, a shared spherical raceway in the outer ring, a cage to secure the balls, and 2 deep groove raceways in the inner ring. They are used in various applications, including conveyor systems, steel rolling mills, and agricultural machinery. In terms of bearing selection parameters, these bearings are notably distinguished for their reliability. Additionally, they offer satisfactory low-noise operation and can be characterized as moderate in terms of rotational accuracy, friction torque, cost-effectiveness, and compactness. Now, let's put their capabilities to the test by illustrating a real-life application. Conveyor belts are essential in industrial operations, serving the critical function of moving materials efficiently and continuously over long distances. Here you observe a conveyor belt transporting rocks from a mine. As you can see, a non-uniform mass distribution of the rocks creates a non-uniform force on the conveyor shafts. This non-uniform force can lead to displacement and misalignment of the shaft. We can address this situation by using self-aligning ball bearings. As mentioned earlier, self-aligning ball bearings consist of 2 rows of balls. This design comes with a distinctive feature. The rolling balls in one row don't precisely align with those in the opposite row, but are centered between the 2 opposing rolling elements. This unique arrangement enables the inner ring, balls and cage to pivot or tilt within the outer ring, automatically correcting any misalignment caused by shaft bending or installation error. Self-aligning ball bearings have a significant capability to compensate for both static and dynamic misalignment of up to 3 degrees. The self-aligning bearing is designed with a small contact angle, making it ideal for handling heavy radial loads while also being able to handle moderate axial and moment loads. Consequently, this makes them particularly suited for applications in mining conveyors where varying load and shock conditions are common. Our last bearing comes with a unique design that can easily be distinguished from other bearings. Thrust roller bearings are a type of specialized bearing specifically engineered to withstand axial loads. The load performance chart of thrust bearings demonstrates their excellent to exemplary ability to handle axial loads. However, they are not intended for radial loads and are also not suitable for managing combined or moment load. They are composed of rolling elements, such as balls or cylindrical rollers, positioned between 2 flat raceway rings and a cage to hold rollers in line. Thrust bearings offer advantages such as their capacity to manage high axial loads and their compact design, making them a particularly great fit in confined spaces like turbochargers, vehicle clutches, aircraft engines, and HVAC systems. Regarding bearing selection parameters, they have satisfactory performance in cost effectiveness, reliability, and compactness. However, they rank moderately in terms of rotational accuracy, noise level, and handling friction torque. Now, let's examine an interesting application example for thrust bearings. Are you familiar with the function of a turbocharger in an internal combustion engine and the crucial role a thrust bearing plays in it? Let's first examine the function of a turbocharger by exploring its inner workings and primary components. A turbocharger in an internal combustion engine is essentially a device that harnesses the energy of exhaust gases to compress the intake air. As illustrated in the animation, the exhaust gas, indicated by red arrows, drives a turbine which in turn rotates a compressor shaft. This compressor then feeds compressed air, shown with blue arrows, into the engine. This compression significantly increases the volume of air entering the engine, thereby boosting the engine's power output for its size. A turbocharger is comprised of 3 main sections: the turbine section, the bearing housing section, and the compressor section. Let's now concentrate on the turbine and compressor sections. The turbine section includes the turbine wheel and its housing, which directs exhaust gas onto the wheel. This exhaust gas imparts energy to the turbine wheel, causing it to rotate and subsequently expelling the gas through an exhaust outlet. In contrast, the compressor section operates oppositely. Here, a forged steel shaft links the compressor wheel to the turbine. As the turbine wheel turns, it drives the compressor wheel, which draws in air at high speed and compresses it. This process in the compressor housing transforms the high-velocity, low-pressure airflow into a high-pressure, low-velocity stream through diffusion. The resulting compressed air is then channeled into the engine, allowing it to consume more fuel and thereby generate increased power. Now, let's examine the main components inside the bearing housing. A thrust bearing, a type of rotary bearing, is primarily designed to accommodate axial loads. As shown in the animation, the thrust roller bearing is strategically positioned directly behind the compressor housing. This placement allows it to withstand the axial force generated by the rotation of both the compressor and turbine wheels. Additionally, to manage the high radial loads, a journal bearing is integrated into the design, addressing the radial forces acting on the shaft. The cylindrical thrust roller bearings are composed of several small cylindrical rollers, held in a cage structure. These rollers are positioned flat, with their axes aligned with the bearing's axis and operate between two flat raceways. Through this animation, we hope to provide you with a clearer understanding of how a turbocharger functions within an engine. In this video series, we have thoroughly explored the 8 most common types of bearings, covering their various aspects and applications. In our next video, we're excited to bring you insights into several special application bearings. These bearings are notable for their unique designs and specialized functions, tailored for specific mechanical systems. If you've enjoyed and learned from our content, please remember to like and subscribe to our channel. Goodbye.